Hello everyone, my name is Logan and welcome back to the lecture hall. For today's video, we are covering the epsilon-delta definition of the limit. And so we're like, the what? Well, the epsilon-delta definition of the limit is just our mathematical real analysis version of a limit. And essentially, well, what does that mean, real analysis? Real analysis is just proving things about real functions. And this is not the proof, but the theorem of what a limit is. It's actually a definition, not a theorem. So we have, let f be a function defined on some open interval x such that st is such that a is inside the set x. Then we say the limit as x approaches a of f of x equals L if for every, that's what this upside down a means, for every epsilon greater than 0, there exists a delta such that if the absolute value of x minus a is greater than 0 and less than delta, then f of x minus L is going to be less than epsilon. And we're like, cool, what the fuck does that mean? Well, let's figure it out. Essentially, what we're doing is, what are limits? Limits are our approach, right? And we approach with our inputs, our x's, and then our y values, and that's where we approach the point where our limit equals. So essentially, we're just checking to make sure that the difference between our x and our a, where we're trying to approach, is going to be very small. And if it is very small, then that means that our f of x minus L, that will also become very small, and thus giving us a limit where both the inputs and outputs approach that point where we have our limit. Let's do an example. Now for our practice problem, we want to prove that the limit as x approaches 3 of 4x minus 5 equals 7. We're like, cool. How do we do that? Well, if we use our epsilon-delta definition, we can prove it. So then if that's going to be greater than 0, x minus 3 is less than delta, then f of x minus L, the absolute value of that, 4x minus 5 minus 7, our limit is going to be less than epsilon. So we just need to find a delta such that it works for this epsilon. How do we do that? Well, we can rewrite this 4x minus 5 minus 7 as 4x minus 12. And that's going to be less than epsilon. And we can rewrite that as 3 times, or not 3, we can rewrite that as 4 times x minus 3, which is less than epsilon. And so, well, we could divide this 4 out, and we get x minus 3 is less than epsilon over 4. So then, if delta equals epsilon over 4, we would prove this. So, so we've done the intro part of our proof. That's figuring out what we need everything to be. So now we actually have to prove it. So we can say, let delta equal epsilon over 4. If delta equals epsilon over 4, then we have x minus 3 is less than epsilon over 4. Then we could show that 4x minus 5, well, we could multiply by 4, we get 4 times x minus 3 is less than epsilon, and then this is equal to 4x minus 12, which is less than epsilon, which is equal to 4x minus 5 minus 7, which is less than epsilon. So we have let our delta equal epsilon over 4. We have our two conditions. X minus 3 is less than delta, and 4x minus 5 minus 7 is less than epsilon. So our limit is proved. So now, what do we do if we have an infinite limit? We know with finite limits we use our epsilon-delta definition, but it doesn't really make any sense to use our epsilon-delta for infinities, because if you approach infinity, how do you do an f of x minus L, which would be less than epsilon? Well, you don't. You actually, it would be stated like so. If the limit as x approaches a of f of x equals infinity, then there exists an m in x such that for every delta in m, if x minus a is less than delta, then f of x is greater than m. So what are we saying here? Well, essentially we're trying to show that if the distance between x and a is very small, or the difference between them is really small, and our function is bigger than a big number, that means our limit will go to infinity. Same sort of thing for negative infinity. If the limit as x approaches a of f of x equals negative infinity, then there exists an n in x such that for every delta in x, if 0 is less than x minus a, which is less than delta, then f of x is less than n. And essentially this is just the opposite way. We're trying to show that if the distance between x and a, the input and the point it's approaching, is very small, and then our function output is very, very, very negative, then our limit would go to negative infinity. So that's everything I wanted to cover in today's video. As always, my name was Logan. Thanks for watching. Have a great day. Bye.